Brief background, this is the publicly owned treatment works sewage treatment plant. It's modeled after that. There's 3 filter presses, and the plates are cleaned between batches. Our team range was between 8 and 20 pounds per minute. Also in the background of the system, this is how the system is laid out. And this is a block diagram of the filter wash system. The theory behind this is with the frequency response, you'll input a baseline and an amplitude, and you'll get your gain, dead time, and time constant. For proportional only, you will have an input of a baseline and proportional gain, input, set point, and change in set point, and you'll get decay ratio, settling time, offset, and overshoot. The proportional interval wasn't put in there on accident. You'll also input your tau, and you will not get the offset or the overshoot. For the steady state operating curve, you see that it's mostly linear. This is the trend line that Excel produced. You can use that to get extra values. This is the FOPDT model for the step up and the step down. This is an example of the frequency response. The amplitude for this one was 4% and a baseline of 39%. There was a frequency of 0.1. For the amplitude ratio average, it's 1.46. It's the average of the amplitude ratio for the 3 curves, and the phase shift average of the 3 curves was negative 48 degrees. For the Bodie plot modeling of the frequency response, you can see that it is a first order system, that you have the ultimate controller gain, or 1 over the ultimate controller gain, the gain of 1.2 pounds per minute per percentage, and the ultimate frequency. This produces a dead time of 59 seconds, that must be an error, that's really large, and the tau of 0.35 seconds. For the modeling, you use these equations for amplitude ratio and phase angle, and this produces a Bodie plot curve that is shown in red over the results shown in blue. This is also with the baseline of 39% and an amplitude of 4. This gives a gain of 1.6 pounds per minute percentage, a dead time of 0.7 seconds, which makes a lot more sense, and a time constant of 0.7, which that should be seconds as well. This is an example of the root locus plot. When you do the root locus results for the system, you get a critically damped value of 0.2, a 1/500th decay of 0.44, a 1/10th decay of 0.99, a quarter decay of 1.3, and an ultimate frequency or ultimate damping of 2.1. For the proportional only modeling, you have this equation where M bar is the controller bias and KC is the controller gain, with E of t being the error. This is an example of the proportional only modeling. For this example, the controller gain is 1.3, the decay ratio is 0.22. You see it's oscillatory and settles down at a time of 5.5 seconds. There's an offset of 0.8 and an overshoot of 9%. For various controller gains, you can see in this table we have K ratio listed as whether or not they're oscillatory or monotonic, as well as the settling times, offsets, and overshoots. Here it is again organized by the controller gains. And then for the experiments, with the same controller gains, we get these values for decay ratio, settling time, offset, and overshoot. This is the experimental decay ratio for proportional only, and then the model for proportional only. Most of the values that are at 0 are because they were not applicable. For the settling time, this blue is the model, and the red is the experiment. If they are 0, it is because they never settled. For the offset values, the red is the experimental and the blue is the model. And as you can see, it generally trends down as your gain goes up. So for the proportional integral model, we had a tau value of 2.3 and then 0.58 and 9.2. These gave gain values that are shown in the tables. This is an example of the proportional integral root locus with those values in the previous table displayed. It also has the ultimate frequency pointed out of 0.4. For the proportional integral experiments, we use the gain values previously shown and the tau values to see decay time, monotonic versus oscillatory settling time. For all of the experiments in this range, everything was monotonic. It was not any that were oscillatory. So this is for the other tau value and the third tau value. Are there any questions?